Good evening, sir.
How are you today?
Sir, very tired and worse.
I didn't get that. I didn't get that.
Very tired and worse.
Oh no. So you are now having what I had.
Sir, what you have?
um, my best days, I guess, are coming ahead of me. I was very hoarse. I had no voice for the last couple of weeks, about 3 weeks to be exact. But I'm getting back now. I'm getting better. Um, as the days pass by. But you'll be fine. Just take your onion line, I guess, and gargle a lot. You should be fine. But so let me ask another question now. So I made a humble request. Nobody not do it. Let me see if I
You have to
really.
tell us so I can find a suitable area to sit down.
This is a suitable area. Hello. On a comma, on a play too rough. I saw they stay a long time. No, seriously, I saw how long did they stay?
We're waiting until they're ready to start.
Well, I'm ready. Thank you, Benika. Thank you, Benvin. Thank you, Miss Asia. Daniela. Will you stay so? Asia, Asia, you're playing
Oh,
rough.
sorry, may I fix the camera? Like, I don't know why. Yeah, may I fix it?
Okay.
May I fix it?
Dan.
Sir?
Don't come from my phone and talk on a pretty sir. You know what you're supposed to do. You don't want to hear no sir. I don't want to hear it. Like seriously, Sammy, Mr. Odin, I really don't want to hear it from you, Like seriously, I don't want to hear it from you. Benika, where you going?
Sir, fixing up the phone.
Yes, Dan. Here, well meet. You are perfect. Benicio, Alexio.
Yes, sir.
You don't understand. Like seriously. Hello, guess what? It thinks if you put on anything else, you look different from how you look. You are you. What is wrong with you? Come on, man. This is the final week of class. Final week of class. I'm waiting. What is wrong? I'm waiting. Dodin, Montague,
Sir.
Marsha. Okay, I'll wait on you, Mr. Dodin. Very good. Montague, unmute for me, please. Dodin. Boy, wanna play rough. Can't keep putting that tongue. Okay, thank you, Denise. So I'm just waiting on Alexia. Downing session from Montague. Can you please unmute for me?
Sir?
Unmute. No man, I'm saying.
Yeah, man.
Yeah man, but where's the video? Where's the video, Montague? Hey, wait for you. I cannot believe that my STEM students are this shy. What is wrong? Come on, Montague, waiting on you. All right, so while Montague put on her eyeliner and her eyelash and come to class to buck those eyes, we are going to begin. All right, so the truth of the matter is, if you are, hold on. So the truth of the matter is, we're on the final lap. We are on the final lap, and I'm pretty pleased for where we are going. I'm pretty pleased for what it is that we have done and are doing. And I'm just hoping and praying that you guys, well, I know you have enough information to go and pass the exam and get an A for the course, but I'm trusting that you guys are doing what it is that you're supposed to be doing in doing your own revisions. Oh Lord. Mikey, why are you laughing, Mikey? Eh? Why are you laughing?
No one was going to open their.
No one crazy. No, he's crazy. They can't do that to me. I mean, see, I trouble Asia, and Asia not in the pain, I mean, you know. No, you can't do that, man.
Is that our fix here?
Oh, you should leave them alone, you know. I'm waiting on Alexa, you know. Alexa is the only one that know Dowding got fix here, but Alexa now pay with a mind. Alexa now pay with no man at all. All right. Yeah, so it's one of those things that we need to just work on in terms of getting our acts together. It's a final lap. It's the final lap. I'm pretty excited. Oh, mosquitoes. I'm pretty excited. I'm excited for what to come. And I'm even more so excited because I went to a place today. And the whole time I'm walking in the place, I was just thinking about my class. Kind of unusual because I mean, the whole time I'm there, I'm saying, oh goodness, the students should be here. So I went to Greenwater today and, you know, taking a tour of the cave, and trust me, I saw a beautiful exposure of calcite. Breathtaking, breathtaking. And, you know, as we spoke about the calcite last class, that it has a lot of medicinal purposes. And the tour guide was able to speak of some of them, and I just smiled to myself and said, yeah. So she was saying, you know, guys, anybody would take Dica? And then I said, Dica? What about magnesium trisilicate? Hold on a minute, please. Magnesium trisilicate solution. All of those are constituents of calcite, medicinally. So you know I said to myself that I'm going to take you guys down there. So you guys need to come to the bachelor's because they say next week is exams. So we're not going to have any time unless we're going to do it after exams. But you know, I really want you guys to see one of the areas that they have inside of the cave is what I call a dead zone. It is highly rich in minerals and an excessive amount of calcium carbonate. inside. But what is so true about it is that that little piece of exposure had life. What do you mean by life, sir? We saw fish swimming around in it. And the mere fact that you have a fish or fish, different types of fish swimming around, that there is life to what it is that we're seeing. Now, she was saying to us that the water you cannot drink the water. And I was like, you can't drink the water. I said, no, man, the water can be had. The water can be had. So I was there and I'm saying to myself, I said, no, man, what do you mean that the water can't drink? I said, no, man, so I need to talk to her afterwards. So afterwards I went to her and I said, what do you mean water can't drink? I just said, no, man, it's too much calcium carbonate. I said, and then she said, unless you purify it. I said, yes. I said, that is the spirit. It has to be purified to take out the extra carbon dioxide, calcium carbonate. When you use your kettle for an extended period of time, and you see that white build up in the bottom of the kettle, people call it chlorine. It really isn't chlorine. What I think it is.
Minerals.
Yeah, which kind of mineral?
Calcium.
Calcium carbonate. So which is why when you add some vinegar to it, or if you add lime juice to it, it dissolves.
Lime juice, yeah.
Yeah, it dissolves it. But guess what can happen? What I normally do at times when I'm cleaning my kettle is just to fill the bottom of it, cover the bottom of it with a little vinegar, and then put it on the stove and cause it to boil. Because remember, I did say to you that temperature increases the rate of a reaction. Remember, we speak about the structure of the earth. Inside the core, the temperature is about 6,700 degrees Celsius. And what it causes is that heat that causes the rocks in the upper part of the mantle to be molten in that sort of liquidy state. So the temperature is very important. It's really very important, and the temperature increases the rate of a reaction. So, and incidentally, what I was saying to her also is that when you look at the aqueduct that collects water that is sent to the Hermitage Dam, what is happening is that it passes through a lot of rocks, and it challenges through a lot of rocks, speaking of a lot more carbonates. So, which is what is called hard water. So we now have to soften the water, and we can soften the water by boiling. We soften the water by boiling, or we also soften water by adding chlorine. So which is what NWC does, by adding their chlorine to the water to purify it, as also to soften it. When we get hard water, what we do with hard water is to boil it. So we can kill the germs and also make it soft, so it's like we don't have all that calcium carbonate. Now let me hasten to say that for us men, we have to be very careful, because the calcium carbonate particles, it is believed that it gives us quote unquote stoppage of water. All right, so we have to be very careful when we are boiling our water. Oftentimes what I do is to strain it, right? Get it to a very, cheesecloth. So it is that you can remove all those particles from it, so that, or allow it to settle, because if the calcium carbonate particles are so heavy, it falls to the bottom. So you just decant, just throw it up, and then you can throw that bit of water, right? So it is that you have good water to drink. So at one point in time in the tour, when we exited the cave, she came out, the tour guide came out and like, anybody knows what is this? And I said, of course, aren't these corals? And then I look up at the structure and like, oh my goodness, these are massive corals. And then nobody that came in mind, of course, we had a whole lot of people that I don't know. And she was asking and nobody answered. And she said, these are corals. I said, no, they have to be corals. And in all of what I was looking for is to see if I could find a fossil in the corals. But I didn't with the naked eye, but trust me. And we also saw a lot of stalactites and stalagmites inside. And it for me, maybe I know you guys will also enjoy it, because of, the introduction to geology that we're doing here. And as environmentalists, we recognize that we have one of many caves within our country that is preserved. I mean, we saw the ratbats. Thank God they stayed where they were supposed to stay, and they never came trying to greet me, or else I would not have been a class tonight. But it is what it is. A very good experience, and I mean, the environment is nice. The environment is really very nice, and I'm very happy that I'm part of the environment here, so that I can share it. One of the things that she said though is that when the mineral, she showed us how alive it is when the mineral was dropping, right? And then it falls at the bottom, and you could see the stalagmite coming up. I was like, wow, I just like it's 100 years. I'm saying to myself, but hold on, my great grandchildren will be alive to see this. So maybe I need to take a picture there and leave it somewhere so that they can see for years to come, generations to come, they can say, see, my great grandfather was here when this thing here was being formed. So this is what life is. If we take care of the environment will take care of us. If we take care of the environment will take care of us. Finally, before we get into what it is that we want to do, I remember her turning off the lights. Oh, Jesus. Me and everyone left the whole of them. It dark. And what came back to mind is this is what our ancestors had to live with, when they're hiding from the enemies, this is what they had to do. And it is because of their doing why you and I are here now enjoying what it is that we're enjoying and freedom for which it is that we are enjoying. So this is it. It's just unfortunate that we really have COVID and we are doing these classes online, because one of the things that we really could have been doing is just going out and looking at structures, bars and folds, and we can look at Trelawney, so we can look at the Feldspar, and we can look at really nice things. I found a rock today. Where's that? Not today. I found a rock yesterday. It's calcium. And while I was there roaming, the geologist inside of me, forgive me. So while I was there roaming, I was there walking, and sometimes you have an inquiring mind. I am there walking, I'm there looking, I'm in deep thought. And I walk and I saw something and I said, oh, this is interesting. And I picked it up and I said to myself, but this couldn't be, because I know what it is. And if this is a case, it means that there is a geological past right here. I said, come on. I'm not in geology mode. I'm in vacation mode. So just leave it alone. And then the following morning, Sunday morning, as a matter of fact, I finished church, and then I was doing another online service. And I said, you know what, let me walk along the beach to just get peace. And I'm there. And then I came up with what, I don't know if anybody can see. Can you see this?
Yes, sir.
What is this?
A coral.
It is a fan coral.
Fan coral.
Right? Yeah. And when I picked up the fan coral, I said to myself, no, sorry. This is interesting. And I walked and I collected about a half a dozen of them. People maybe on the beach and said, this man is crazy. Didn't care. And I picked them up and I looked at it. And then I remember standing, and then Spirit of the Lord, I believe, said to me, look down. And when I look down, I'm saying to myself, Jaja, I'm standing on a dead coral reef. And when I looked around and I looked at the rocks, I was like, but these are corals. And when I looked around, then I saw one whole host of fan corals washed ashore. And I'm saying to myself, can't believe that these people are doing this to the environment. And I remember going to the pool and I saw, well, a little kid was in the pool. And then I said to him, I said, what is your name? And then I recognized that he was autistic. So his father came over and says, he's autistic. I said, yes, I kind of figured. I'm figuring because I'm hearing the speech. And then we started talking. He was on campus with us, well, with me. Never met him before. He's a geographer. And we started calling names that we recognize that we have mutual friends. I was like, strange. And then he said something to me and I wanted to verify, one of our team members passed. So I had to call Walter. I said, Walter, you didn't know about this? He said, yeah, man, Sean, sorry, man, I tell you, Walter, I can't do this because they put me some years. That's fine. I said, yeah, man. And then the person said, who that? Noel? I said, tweet. It was just one big celebration. And we were having a conversation. And as a geographer, I said to him that I'm pretty upset for what is happening because when these hotels are being built and these housing schemes that are being built along the shore, the man them are damaging the environment. This is where you are going to come into play as a geological engineer, as an environmental geologist, as an environmentalist, whatever no one calls themselves. This is where you're. When I'm sitting there and trying to just live, you are the ones who are going to take over this stuff. And I said to the individual, this is why I will never get into environmental policy. Because if I got into environmental policy, this very place that you and I are standing on would never get approval to be built. And the individual said to me, take time and talk. Because, and then I remember what Michael said.
Which location that's, sir?
In Sentan. Yes, ma'am.
By
Very, very, very close by. I mean, like a stone throw away.
I know exactly where you're talking, and
Yeah,
I know the story around that approval.
Stone throw away. And then I remember what Mikey said in class. And I'm going to remind you what Michael said in class. And I said to him, I said, Michael, why come to class to come disturb this, my peace? Mikey said, sir, you can go and stay to talk about how the government not doing anything to build Anchor. You don't know who these people are, right? And what it is that they're getting. And it's just true. I knew this from before. And one of the things, is when you are in leadership, and Mikey comes to me and said, boy, Sir Shan, say, I have a plan, I have a piece of land right here, so it is only such and such a square, feet, and but I want to put up a little hotel, But it would mean now that I have to go build up a section of the ocean so that I can extend it and increase the square footage because we really want to go 3 stories. We're going to get the geological engineers to come to just test the soil, and chances are we have to go compact it and we have to go drill down and do some engineering stuff so it is that the foundation is strong. But I want you to just pass a thing or two and I say, boy, you can't do that. I say, no worry about it, man. You're good because, say, I also build some set of apartments down the road. Because one of them apartments are yours. And then I may look and say, Michael, stop laughing. I may look and say, think about it. Out of all of this, I can get a I can get a summer house or I can get a little whatever it is. I'm saying, all right, here the plan. So forth and so on. Me get in I'm working with the government, and out of it now, I'm gonna get something, conflict of interest. But I will now give approval because at the end of the day, somebody building something and I don't have to declare it because it's a gift. I may have a summer house. Guess what? That is something that is easy, 50, $60 million. That now is going to increase my asset. So therefore, I'm just going to put my signature on paper and I'll sign off and say, well, go build the hotel, you're good to go. And then me say, yo man, when NEPA come in and NEPA say, I said, no, and get the approval. We know that we have the engineers to go ahead and do that support and so on, bam, 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 bam. Done. What it is that we have done is to damage the environment. I've seen so many evidence of it. And this weekend has been fun-filled, but one filled with a lot of reflections on what it is that we have been doing. And we have done quite a bit of wrongs. When I see those dead coral reefs, let me tell you what it says to me. That at some point in time in our geological past, all of that area was covered with water. Coral reef don't occur in shallow water, true or false? Question. You think you can find coral reef in shallow water?
No, sir.
No.
No. A deep water, me I talk about water where you can't stand up in. And when I can see that I'm standing on the corals itself, and I look around, and when I look around and I see the monstrosity of buildings around, I'm saying to myself, global warming is really in effect. Water is indeed receding. And what is going to happen? The final thing I'm going to say. So yesterday evening, I went out on one of the barge that was built. Vexboard actually, you know, Vexboard, but I went out and I sat down. And when I looked, I heard something behind me. So I turn around because me I hear them talk about them find mermaid in Africa. I say, no mermaid now go hold me, don't notice. So me know so me not dead. No mermaid now. So me look around, I say, I look. You know, the waves will normally come parallel to the shore. Anybody ever see the wave normally comes? Do you agree with me that the waves normally come parallel to the shore? Yeah, man, when the waves come, if you're in the water, the waves will almost come directly at you. In this particular case, the wave was not coming parallel to the shore. It was at an angle. And the angle that it was at, it was beating on the side of the banking. And the only reason it was unable to come directly parallel to the shore is because of how they have built some groins. You know, them metal cakes, something that were filled with conglomerates, call them groins. They have built some groins. So it now creates a false backing. So the wave no longer comes parallel. It goes at an angle. And I'm telling you, in a couple of years, it's that shoreline that is going at an angle, it is going to erode. They will now have to build groins in order to contain, because at some point in time, those mangroves that had a purpose to keep the soil together, and it is a habitat for what? The mangroves are habitats for what?
Nursery fish, baby fishes.
As also, say crocodiles.
Crocodile.
Yeah, man.
Crocodile.
Yeah, man. So you're right. So the baby fish, so that the big fish can come inside there and eat them out. But it is also habitat for crocodiles. So what is going to happen? We're going to have more crocodiles walking land. It becomes dangerous. So I'm saying this to say to you when you get your exam paper, don't expect to see a question like, I'm just pulling something out of the bat. Write an essay on creationism or uniformitarianism, for argument's sake, where you can just go and put in that in Google and you see something comes up on creationism or uniformitarianism. No, expect to see what is creationism. Give 2 or 3 or 4 or 5 or 10 examples of creationism that you can relate to now. So you have to understand that concept and able to relate it to it. As a matter of fact, I could ask you, what is uniformitarianism, and give you 2 examples of uniformitarianism. And you will know how to go and find examples in our today's world of what uniformitarianism is. All right. So I say this to say to you, I'm preparing you for when you go out into the world of work. Now, some of you may find jobs on your own. Some of you may open a consultancy business, but some of you may also go into policy. Pat sounds like he's one of the most likely candidates to go into policy. I pray to God that Michael does not go into policy, because if Michael goes into policy, then we're going to hunt Michael, because Michael is really decides that film signature now go upon nothing, and the man them going want to look for him. And since we don't want them look for him, we don't want him in a policy. But I'm like Michael, they would want to look for me also. So I am not wanting to go into policy, because there are some things that I will say, nope. You saw them mining will take place in a St. Thomas? It will be a no. It will be a no, right? So I expect that some of you will work at the forestry department, where you're going to be called to look at those dated trees. This is what is going to happen, which is that you're going to help to preserve the forest. Some of you are going to be called to work at NIPA, where you're going to be called to areas where, because by right, when there's going to be a development, that these environmental agencies must be called for them to do their EIAs. Anybody knows about that? Because I'm sure you've been EIA now. True or false?
True.
All right. So you have to do your EIAs in order to make sure that the environmental impact is reduced or can be mitigated. So you're moving 5 trees. What is going to be your response? Your response is to plant 10, so that you're damaging, but you're restoring. It is what I'm saying, because we understand that we have to do some of these things in order to develop the country, right? Like cutting the highway. Kind of sad about that, but I understand that we needed to do something like that, because we really had a combusted journey moving from Kingston to Ocho Rios, driving on Mount Russell. So the highways was very necessary. But what should happen? We now should look at the lithosphere that will cut through, that we should be tying back, so that at least we're preserving. We don't have these fractures and these faults that are open to weathering, so that these faults can now break away and form land slippage, right? So these are things that the environmental agency should really come into play, and should be saying that, okay, now that we've done this, we have assessed here, this is what is happening, this is what needs to be done, so that we can preserve the environment. So it's a whole lot. And I mean, what I want you guys to do is to really focus on the courses that you're doing. There is a market out there for you. When I said to you that there are jobs out there right about now, you can go into the hotels to find a job as an environmentalist. So you will say to them, this is how we are going to be disposing of our waste. So them peel them banana and them yam and them vegetable and support and so on. You as the environmentalist is going to find a section of the hotel that you're going to have your compost. And you're going to get the compost because you know, so the hotel have pretty plants. Talk truth. Talk to me. More to know that we're not live in class tonight. Yeah, no?
Yes, sir.
So when you
Yeah,
have
man,
your
pretty plant.
yeah, man. So when you have your soil rich in potassium, rich in nitrogen, rich soil, right? Your NPK, right? And your phosphorus, and you throw a little of that compost under your plant root. Who's a pretty? Yeah, man. Right? So this is how we are going to be using this stuff. So what can also happen is in the hotel now, you can say the gray water coming directly from your shower or your face basin, how it is that we are going to create a catchment area. So we can use the gray water for irrigation instead of using potable water. That is going to be your task. That is going to be your task. And if you can do something like this, one, the hotel will recognize a lower water bill. You're saving the environment. You're recycling. It does a whole host of things, right? So as it relates to your sewage, how are you going to be dealing with it? Wastewater management is a course that I know you guys would have already completed, and you will know about the primary, secondary, and tertiary stages in treating sewage. Tell me that you did that already, right?
Yes, sir.
Absolutely, yeah, man. Right? So you know that in your secondary stage, you use your secondary stage mainly for irrigation purposes. But in your tertiary stage, where it is that you are going to be bleaching for E. coli and F. coli and also, all of that goes back into the water system. When you bathe in it, we swim in it, we drink it, we cook with it, we wash with it. Yes. So it is an area that needs a lot of bright minds like yours. And I'm saying to you, don't be slavish to just reading the information. See how it is that you can apply the information to today's life. And as such, one of the things that I want us to talk about tonight is the whole business of radiometric dating. As I said before, we're wrapping, and radiometric dating is really the process of determining if one rock or the geologic event is older or younger, right? Without knowing their specific ages. So you are going to be looking at some exposures and you can guesstimate that, okay, this one is older than the other. And you're just going to be stacking the information and just, naming that oldest, second oldest, support and so on. And then of course, your exposure on top is going to be the youngest of them all. I'm going to share something to show you an example of what it is that we're talking about in terms of. So if you're looking at some relative dating principles, and I am going to be sending this in the link for you so that you can have a look at it. When you're looking at your relative dating, you would agree with me that the exposure at the base here is going to be older than the exposure up top. Talk true. Yeah, no?
That's the expectation.
That's the expectation. And this is what we call stratification, right? So the stratigraphy graph is going to show you the layered sedimentary rocks. So over time, the first set, the lower pieces will be the first set of deposits, And as time progresses, you're going to have more deposits and more deposits and more deposits. And what is going to happen? And you can see the different layers right here. Now, it says this section discusses principles of relative time used for all geometry, but especially useful in stratigraphy right here. So when you look at all of this, one may say then, sir, if this is sea level, how it is that you're able to get all of there? And then one may say sea level could have been here at one point in time, or it could have been here at one point in time. One may say then, sir, how up here is formed? You have things like tsunamis that will contain different deposits that when it passes over here, what it does is to leave deposits as it goes along, right? So this is how it is that we can look at our relative dating as well. We look at principles of superposition, right? Undisturbed sequence of sedimentary strata, and the layers at the bottom, of course, will be the oldest, and the layers above are going to be the youngest parts. And if you look at this lateral continuity here, you see different layers in this region. And let me see if I can bigify it. So if you even look across here, you can see clearly that the sections over this side has some relation to the section here because it all looks as if it is one line. True or false?
True, sir.
Yeah, man. Right. So you can, and by extension, this piece over here looks like it's a part of this piece right here. Like everything here was in one. Everything here was in one, right? One may say, then sir, what happens right here? We don't know. It could be a crater that was generated from some volcanic activity. It could be anything in our geological past that could cause this sort of crater that you're seeing right here. Right, could be that, right?
Or the crater.
Yeah, the crater. So in this section here that we're looking at, it could be a crater. It could be something. It could be anything, right?
Land
slippage, and it could also be on a fault line. It could also be on a fault line where you could have the dip strike, you could have the lateral movement, you could have an oblique fault, something that is going to disturb the movement of the outcrop there. And then this one here is a dike cutting across the older rock, right? So you're gonna have this dike right here. And it says here, the lighter of which is younger than the gray rock. So it's cutting across. So this piece here is going to be younger than the other pieces of rocks that are outside there, right? So I'm going to send you this, so it is that you can look at it. I'm just speaking about the matter and then showing you some photographs to bring across my point. So if you look at the fossil succession showing the correlation among strata, now when you use the word correlation, it means that you're comparing two or more things, all right? Now, I'll go back to the geology of Cuba compared to the geology of Jamaica. There are some fossils in Cuba that are exactly the ones that are found in Jamaica. You have some exposure in Cuba that is also found in Jamaica. So as I showed you before, it seems as if everything was just one massive piece until we had some great catastrophe that took place that broke it apart, as we discussed previously. Because if you look at the animation based on the location of Jamaica, if you look at the animation, you can see where all the pieces will come and fit together in order to form one massive structure, right? So that breakaway could have been a meteorite. It could have been some catastrophic event that took place, that broke it up. And it is believed that geologically, there is some relationship between some of the countries that have broken away. So the geology of Cuba, as I said before, Jamaica, are pretty similar. If you look at it, if you read some of the literature, you'll find out that some of the exposures found And the mineralogy also found in Cuba are exactly the same as those found in Jamaica. So this is what they do. So they're actually correlating. So they say,
Central
okay,
America
fine.
too.
And Central America as well. Absolutely. Venezuela, all the regions in that Great Antillean Islands, the Less Antillean Islands, the ABC Islands, right? Aruba, Bonaire, Curacao, all of those islands contain similar structure that will suggest some geological relationship, right? So what course was that? Caribbean geology. There was a course that we had to do. Caribbean geology. Just think about it. You're now doing an introductory course in geology. We had to do Caribbean geology where we studied countries within the Caribbean, and we have to look at similarities and differences to see which countries did not, or really don't follow the geology across, and we had to look at those countries that had similar geological connections. So we had to look at the geology of the Caribbean, and that wasn't a nice book to read because all you're seeing is just black and white, and you had to be using your imagination to see, think of what it is that they're referring. So when you look at things like, when you look at these exposure, you're going to go, and this is why field mapping is very important, because when you map and you take samples and you look at exposures and you take the dip and the strike, and you look for fault lines and you look at the mineralogy and you look at folds and you look at fractures, and then you map the whole area, the type of rocks that you're finding there. Is it igneous? Is it metamorphic? Is it sedimentary? So you're mapping the geology of one area. What is also going to happen is when you move to another area, you're also mapping the geology. When you map both areas and the geology comes into play, you may say, something is happening here. And it's like a puzzle that you're putting together, because you may find an area that is very well layered and you're not seeing any faults, but you're going to another area where you are going to see a dip strike fault, right? Where they're hanging one on the footwall, and you can say, but hold on here, there's a fault line that goes right here, but it so happens that the fault line stops here, but does not extend over to this part, right? So you are now able to put on a map geologically where you expect the fault to stop. And this is what it is that you are doing. And this is your hypothesis. And then other geologists now may go and test your hypothesis. And if they come up with something, they say, yes, we agree with Asia, we agree with Benica, we agree with Mikey, we agree with anybody else. And then no, you may have people who come and say, no, I disagree. And this is how the whole business of geology is. Somebody goes out there and put a hypothesis together, and then you have somebody who's going to say, here, Brad, let me go and just test this hypothesis to see if it makes any sense. And they test a hypothesis and they agree with you and they say, yeah, it's true, I agree with him. And then somebody may come and say, no, but I disagree because X, Y, Z. Hello? Oh, I thought somebody was coming in, right? So this is how it is that we're going to be looking and able now to map the geology of the whole area, similar to what it is that we did when we mapped the central inland of Jamaica. What the university did was to split us up in, I think, 3 groups. I think there were 3 groups of us. 3, yeah, because not very many of us that went to final year. It could be about less than 10 of us that went to final year. And we had groups of 2s, groups of 3s that we had to map the central inland. So each person had a different section. And what the lecturer did afterwards is to look at our readings. And if we thought we're just going to go into the field and cook it, believe it or not, the lecturer will say to you that, okay, I am going to be visiting with you on a particular day, and I want to see your field work. I want to see your notes with your dip and strike readings, and I want to see the areas that you've already covered on your map. And we have to show him. I remember when he came, he says, hey, you guys covering a lot of grounds. And then when we're finished and went back to school, what we had to do was to put the information together. And what the teaching lecturer did was to use our information and did a publication on its own. And I think that is very unfair because none of our names were mentioned in that publication. But this is how it is that we develop in
Wait,
geology.
sir, I know that feeling, the bad.
No, man, trust me. I have done the field work. I was the one who went into the field and walked into cold down and get covered with ticks and had to use tweezers and take out ticks, silver ticks out of my toe. And we did the field work, but they got the results and they did the stuff. But nonetheless, I'm very happy because I was able to contribute to the development of those areas. So if you look at it, so we can have, so this is what I was explaining earlier. So you may have some conformity going here, and you see the exposure here is the same exposure as here. So you may have this conformity here, then you may have a non-conformity here because they have a different exposure here, or you may have something angular here. So when you look at one area, you may say, hey, I saw some levels of disconformity here, but the exposure here is the same exposure as here, which is the same exposure as here. And then you can draw a conclusion to say something took place. There's a dike somewhere, there is a fault somewhere, there is something that is taking place. So, something like this is very possible. So this here is going to be your dike. This, of course, is going to be your fault line. This here is another fault. And there are several things that you can. I'm seeing a river that is running somewhere here. This could be another fault that you have. Well, this is the same fault from here, where we have the hanging wall down here. This piece dropped down. This piece remains. That's the foot wall, and you can see the exposure here. So you should be able to look at one of these block diagrams to apply the relative dating principles of what is really happening, what you think is taking place in this exposure, right? So that's one area. Asia, I'm going to call upon you because there's something that I really want you to look at. Play for me. So when you talk about the radiometric dating now, as I made mention earlier on, you're going to be using a lot of half-lives. For the radiometric dating, our commonly used elements are uranium-238, 235. We use potassium also, but we also use carbon-14. So carbon-14 is heavily used in our radiometric dating process, similar to the uranium-238, 235. All right, but these are other radioactive. Yes, sir.
Why is it that the uranium-238, 235, why is it that there is limited usage of that and more carbon-14?
It's good question. I think the carbon-14 is, well, part of the problem with the uranium is that it gives off quite a bit of lead. And we're talking about the whole business of lead poisoning, that has a lot of developmental issues, among the young. Carbon-14, one of the byproducts will be nitrogen that has quite a bit of usage. If you can recall, nitrogen is one of those common and useful elements in terms of plant growth. So nitrogen is very, very, very important. It is also a starting reagent for many important chemicals that we use. One of the byproducts from the visit of the cave today was ammonia from the poop of the rat bats. Another important starting reagent for many things, many chemical products. All right. And carbon-14 is also used, for previously living things. So when it is that you're doing, things that once lived, your fossils, dinosaurs, when we find those remains, we use a carbon-14 really. So if it is that you're looking at a rock, maybe an igneous rock or a feldspar that you'll find, and you want to date that feldspar, you are going to be using potassium 14, right? Because you use it to date rock forming minerals, for argument's sake.
40.
Right. Rubidium is another one that you're going to be using for dating rock, right? So, but most of the stuff, what we use now is just as it says, is really mainly carbon 14, because those are once living things. Mummies, coal, peat, the coal mines. You have these mummified stuff that you find, carbon 14, because they were once living creatures. All right. So, but the others are in use, So you just need to know that for the carbon 14 for those previously living things, and if it is that you're doing rock formation, it's going to be either rubidium, or it is that you're going to be using your potassium. And some of these byproducts, as I said before, has its usage, right? One of the other things that is very important is when you're talking about a rock formation, when you look at the structure of the earth, the rock exposure is not 5 years old. You talk about billions of years old, right? So this year goes, their half-life in years go up to 1.25 billion. So if you expect a rock to be older than this, we won't use potassium 40. We'll go ahead and use rubidium for rubidium 87, right? And if we believe now that it is older than that, we're then going to move to uranium 238, uranium 235. So depending on our guesstimation of the age of the exposure, we will know what to use in order to determine its half-life. All right. So and if you look at it, you'll recognize that the dated materials here are pretty similar. Right? Muscovite biotite, whole crushed volcanic rocks. Here, the condition, the dated materials here and here are pretty much the same. However, one may be older than the other, right? So 1.25 billion years, we can say here the plant, potassium 40. But if we think that it's going to be older, then we're going to go to the rubidium, right? Things that are much younger is going to be carbon 14, right? So you talk about like if, as I say, your mummified stuff. We don't, sometimes we may say, they may be 106 billion years ago. So it is, I'm going to ask you, I'm just giving you the overview because I'm going to give you this to read. It's very interesting, right? Now, goodness gracious. Asia, I want you to play this for me, please, because I don't know, I can't play it. Cannot seem to be playing anything, but guess what? Oh, crap. Hold on a minute, please. I didn't do this. Let me just stop share. So I want you guys to see what it is, because I have not done any chemistry review in this course. And it's important for me to introduce you to some levels of chemistry, the atom itself in particular. What am I looking for? The atom itself in particular. And the whole structure of it. And I think this is it that I want. Is it so just play for me? I'm trying to get the link. Copy. Yeah, so it is interesting. When you move into different labs, Asia, there you go. Let me know when you you're ready. I'll just speak until you can go ahead and share for me. When you go into different labs in the States, and you see how they operate, it brings the geology to life. We don't really have that sort of that level testing here in Jamaica. Um, so it becomes a little mundane because you really can't relate. You just have to read and just imagine. But when you're able to do the test, in a lab itself and see what is happening. For example, when we're looking at BODs and CODs, the oxygen levels in water, you may say, oh, this is what it is. But when you really get the readings, you may find out something different. All right. So I'm going to ask you to play and then just listen to me, Asia. I may stop you at different points just to go through it a little bit more explanation. Go ahead for me, please.
Ever wonder how scientists concluded the age of the Earth to be about 4.6 billion years old? Or how geologists determined the ages of caverns, rocks, volcanoes, the Himalayas, or even the age of Pompeii bread? Well, scientists are able to answer all of these wondrous questions and more by use of a process called radiometric or radioactive dating. Radioactive dating enables geologists to record the history of the Earth and its events, such as the dinosaur era, within what they call the geologic timescale. Radioactive dating uses the ratios of isotopes and their specific decay products to determine the ages of rocks, fossils, and other substances. Elements occur naturally in the Earth, and it can tell us a lot about its past. Carbon, uranium, and potassium are just a few examples of elements used in radioactive dating. Each element is made up of atoms, and within each atom is a central particle called a nucleus. Within the nucleus, we find neutrons and protons.
All right, I'm going to ask you to go back just before they expand the. No, come a little forward. Come a little forward. Right. No, come on. Go forward. Go forward. Go forward. Right. Stop right there. All right. So this is what I didn't do with you, and I just want to give you the background information on it. So that's an atom. In that inside piece there, the centerpiece is called the nucleus. The nucleus of the atom is the brainchild. This is where everything that we do takes place within our brain. So if we are going to be lifting our hand subconsciously, that decision was already made in our head space. All right. So that's the brain of the atom itself. All those little blue things that are marked E in those rings are electrons. They sit in orbitals and they spin. Sir, spin. Then how them just stay afloat like that? They're not gonna drop out. No, because electrons are negatively charged. Electrons are negative charged, and this is how, when you and I touch, well, not me and you, when you touch an electric wire, you get electrocuted. I know how I will not die, because once I see that I'm not going to be touching it, it's because our blood is also charged. Our blood is positively charged. All right. And when the electrons are running inside of those electric wires, the positive and the negative love each other, them French kiss, and it just draw out the stuff. So which is why we fry, which is why people fry when they get electrocuted. All right. So God forbid, I saw something recently of a JPS worker who was electrocuted, and he was just hanging in midair on one of those electric wires. And I'm saying to myself, there was a man who was trying to feed his family, and unfortunately he, got electrocuted. Maybe something he just never did what it is that he was supposed to be. I won't die that way, because I know I ain't doing those jobs. All right. So you look at those things, the nucleus is positively charged. The nucleus is positively charged. So there is an attraction between the nucleus, the center part, and those elements, the electrons that are orbiting around the nucleus. In the nucleus contain my protons and my neutrons. My protons and my neutrons. Now, there's a relationship between the protons and the neutrons. They stick together as in a relationship, because when you look at the electronic configuration of some of the elements, Asia, go back for me, please, hon. Go back until you see the periodic table. Go back, right, stop right there, thanks. When you look at the periodic table, hydrogen, then over here, number 2 is helium, then lithium, beryllium, boron, carbon, nitrogen, oxygen, so forth and so on. When you look at something like chlorine, number 17, the electronic configuration of chlorine is going to be 2, 8, 7. 2 plus 8 is 10 plus 7 is 17. The first shell can hold a maximum of 2 electrons. The second shell holds a maximum of 8 electrons. The third shell holds a maximum of 8 electrons also, right? The K, the L, and the M shell. So what happens is similar to what I showed you just now. So when I put the electronic configuration as 2, 8, 7, it is saying to me that in order for that chlorine to form a bond with hydrogen, for argument's sake, to form hydrogen chloride, HCl, it means that chlorine is going to accept 1 electron. Now, hydrogen, the first one, has only 1 electron to give. So there's going to be a bond between hydrogen and chlorine to form that sort of HCl bond. Now, what is happening is, because chlorine is accepting 1 more electron from hydrogen, or not accepting, but sharing that 1 electron from hydrogen, there is going to be, chlorine must become ionized. So what chlorine now has is not 2, 8, 7, but 2, 8, 8. I'm seeing some faces looking at me as if, what is Sir talking about? So I hope this doesn't take long. I'm booting up another system so that I can show you exactly what is happening. So there is no way you can do geology without not having some basic knowledge of chemistry to it, because you have to understand how the chemistry works. The identification of minerals, for argument's sake, calcite, right, is one such mineral that we need to know about. Calcium carbonate. How does calcium carbonate comes about? Calcium carbonate is a combination of calcium, which is number 20, with oxygen, which is number 8, which is and carbon, and it is arranged in different ratios to form this CaCO3, and all of that now will give you your calcium carbonate. So it works in tandem with the elements of the periodic table to form compounds. So when you're looking at things like your hydrochloric acid, your HCl, it is going to be your hydrogen linking with your chlorine in order to form that HCl. When you talk about your sodium, your sulfuric acid, your H2SO4, it's your hydrogen with your sulfur with your oxygen, and it is relating into a particular ratio, right? So it is that you can tell exactly what is happening. As I figured, this other system is going to take a while to come up with. Asia, I'm going to ask that you continue the video. Hopefully by then, it will free up somewhat so I can show you exactly what it is, the structure that it is I want to show you. So scroll forward for me, please, Asia. Let me look at the circle, right? So when you reach there, what you find is that it's going to tell you about the relationship with the neutrons and the protons, and it's going to tell you the relationship of those with the electrons. Why is it that the electrons are in the sort of ratio that they're in, and those that are going to be stable, those that are unstable. So when you look at uranium-238 versus uranium-235, you'll recognize one is 235, one is 238. That means one has more electrons than the other. Now, because it has more electrons than the other, it then becomes very stable, very reactive. And that reactivity now causes it to be very dangerous, extremely dangerous, because it has the carbon-12 and the carbon-14. So when you look at carbon-12, carbon-14, you have 2 more electrons in the carbon-14. It becomes very unstable, and you can do what's here, it's gone. You can do many other things with it. All right, continue playing for me, please, Asia. Let me see if I can fix this business. Go ahead for me.
And within each atom is a central particle called a nucleus. Within the nucleus, we find neutrons and protons, but for now, let's just focus on the neutrons. These neutrons can become unstable, and when they do, they release energy and undergo decay. Scientists call this behavior radioactivity. Radioactivity occurs when the nucleus contains an excess amount of neutrons. When an atom varies in the number of neutrons, the variation is called an isotope. Isotopes are unstable forms of elements. During radioactivity, the unstable isotope breaks down and changes into a different substance. A new, more stable isotope called the decay or daughter product takes its place. The isotope doesn't actually deteriorate, it just changes into something else. Isotopes decay at a constant rate, known as the half-life. The half-life is the amount of time it takes for half of the atoms of a specific isotope to decay.
All right, don't worry about that. Never mind. You can stop, Asia. It's just for marketing purposes. All right, thanks. So that's what it is saying. So these isotopes are atoms of the same elements with the same number of protons, but different number of electrons. So protons and electrons are exactly the same. So in a normal atom, the number of protons equals the number of electrons. But for an isotope, the number of protons, the number of electrons will be more than the number of protons, right? So it becomes very unstable. Now you're going to have half-lives being formed. You're going to have half-lives being formed. And these half-lives will tell you now what comparisons of the age of different structures that you're actually dating, right? So you will have standard known half-lives that it will say to you, okay, the reading is very close to this reading. So you can say, oh, this happened 65 million years ago. So that's how you read the half-lives. And as I think I said this to you before, and let me say it again. You know, when you have a child, or maybe you wouldn't know, but when a child is born, there is a normal growth curve that is used. And this growth curve will tell the doctor if your child is growing normally or abnormally. There's also a weight curve, which will tell you whether or not the child has the correct BMI or the child is obese, overweight. And so what the doctors will do is that when you go to do your checkup, the doctors will say that, okay, how old is the child, mommy, daddy? You say 6 months old. Okay, 6 months old. You look at the weight of the child, you're going to look at the height of the child, and you're going to do all of those stuff. And you're going to look at it, you're going to map it. You say, okay, generally, normally, the child who weighs 25 pounds should be at a particular height. Now, if it falls within a range, you'll say that, mommy, daddy, your child is growing normally. But if the weight is supposed to be 25 pounds, but that child is weighing 60 pounds, you're going to say, hold on, give him one less dumpling, one less piece of chicken, because the pity didn't yam too much. That's exactly how the half-lives, oh crap, from the whole weekend, this system here is just giving me problems, honestly. And that's why I can't share my stuff, because normally I'll be able to share my videos with the sound, but I'm using another device that don't permit me, and this thing here takes forever to come up. So what happens is that in the system, there are known half-lives that when you go and you date the stuff, it matches to some half-life and it tells you what age it is. Now, the truth of the matter is, you may find an exposure and you say, hey, I'm going to date this rock. And then you get a particular date, and then somebody decides that I am going to do this, because this is why it is very important for you to research. Sorry, this is why Darwin and Hutton and Lyell and all these people were able to come, and one can critique the other, because when one finding comes out and say, here, I'm going to check to see if his hypothesis makes sense. And then this is what they do, and they compare and they say, hey, I am more tending to what this person is saying, because this thing here is making a lot of sense. All right. So I wanted to draw something for you, but that is really not working with me at all. Let me see if I can use a whiteboard here. All right, let me attempt something here. All right. So in the center there, I have my protons and my neutrons. All right. Let me look at sodium for argument's sake. Sodium, the mass number is 23. The number of electrons, the number of protons is equal to 11. So that's how we write it. We write the mass number up top, the number of protons and number of electrons at the bottom there, which is 11. Now, it means that I have 11 electrons. Now, the electronic configuration of this is going to be 2, 8, 1. It means on the first shell, I'm going to have 2 electrons. The second shell, I'm going to have 8. 1, and it normally appears in pairs. 4, 5, 6, 7, 8. And then the last one has 1. So I have 11 electrons, right? So all those X's are representing my electrons, all right? Now, the number of protons equal the number of electrons. So it means then that my P is going to be equal to 11, because the number of protons equals the number of electrons. This here tells me how many electrons I have, and the number of electrons and protons are the same. So therefore, the number of neutrons is going to be the sum of that, because the mass number is my protons plus my neutrons. So my protons plus my neutrons give me my mass number. So if the number of protons is 11, how many neutrons do you think is contained in sodium?
12.
12. So I have 12 neutrons. I have 12 neutrons. Now, so what is, so the neutrons are neutrons, neutral, right? Neutral, neutrons, neutral, 0 charge. The protons are positively charged. The electrons are negatively charged. So look at what I'm talking about. So if the protons equals the number of electrons, 11 and 11, it means that it is in equilibrium. True or false? Talk to me now.
Sir, repeat the question, please.
So I'm saying if I have 11 protons and 11 electrons, it means that I have an equal number. So them natural out.
The balance,
Because,
yeah.
Yeah, man. Right, good. Work with me, man. Work with me. I don't want to lose you. Now, when I'm speaking about an ionization, it means that sodium is going to give up that one electron, because it is easier for sodium to give up that one electron than it is to accept 7 other electrons. So when it does that, sodium is going to form a charge of Na plus. One may say, how did it form that Na plus? It forms the Na plus. Sir, plus means positive, don't? Absolutely. So when I remove that electron that is circled, how many electrons do I now have in my sodium? Somebody said 10.
10.
10.
10, very good. So I have 10 electrons, all right? How many protons do I still have?
11.
11. Let us do some mathematics. Protons are positively charged, electrons are negatively charged. So 11 minus 10 equals?
1.
What kind of one? Positive one or
Minus
negative
1.
one?
Minus 1.
Remember the protons is 11, you know, and the electrons negative.
Oh, yeah. 1,
So
positive
11
1.
minus 10, right, so you get positive 1. So I have positive 1. I have positive 1. It means that I have 1 thing. So this is what is happening. So I can tell you that my sodium atom is going to be positively charged. My sodium atom is going to be positively charged, because where it is that I had some equilibrium, the number of electrons is equal to the number of protons, 11 and 11. When sodium ionizes and it loses 1 electron, it gives up 1 electron, it means that it now has 10. And with its 10, it means that the number of protons cannot change, because the protons and the neutron, they are inside the nucleus of the atom. You and I cannot get to the nucleus of the atom. That can't change. So the atom becomes positively charged. Now, what happens to those that forms an isotope? They are atoms of the same element with the same number of protons, but different number of neutrons. And that's what causes the reactivity of these atoms. Very reactive, extremely reactive. They react explosively. This sodium ion, you see, because it is so charged, it reacts explosively. Matter of fact, if you put, if it is raining and you get a piece of sodium metal, and you throw it out in the water there, it is going to react almost explosively, because it is very reactive. Pulls the water from it and it's going to form sodium hydroxide. Right? So I'm just showing you how it is that we form these we call them now isotopes. This is how you form these isotopes. The isotopes are formed based on the addition of these extra electrons. Uranium-238, uranium-235. One has 3 more than the other. Carbon-12, carbon-14. One has 2 more than the other. And the more it has, it is pushing things out of equilibrium. It becomes much more reactive. All right? Any questions so far?
So,
Are you following?
explain exactly what the isotope is, as I didn't catch that part.
All right, coming to you. Let me just stop here. Right here. Hold on. Let's see, no. I see my screen? No, yeah.
Nothing is up as yet.
Okay. Not coming. I'm trying to find. What are you asking me? Ask me how is it that how is it that the isotopes are used to do the dating, or what is
Correct.
it exactly?
Well, both, because you just mentioned that when the atom loses the electron, it becomes charged.
Mhm.
So I'm asking, how firstly, what is the isotope and how is it used to do the dating?
All right, so the isotope is going to be share screen. The isotope is going to be oh Lord, remember what it is at the video. And you and when I send you the link, well, the link that I just sent in the group, when you look at it, you will see you can click on student, and what it will do for you is to show you, is to continue with the video. All right. The uranium 238, the uranium 235. Anybody can. Oh Lord.
Zero chemistry background, you know, so that's why.
No, that's fine. I was gonna ask Asia to Asia, can you put about the video for me, please, and just project the periodic table? I just want to bring something for you. Good question. I just want to, my sharing device is not coming up, so which is why I'm depending. All right, go back in that video for me, please. Go back in that video. Scroll back. It's not allowing you to go back.
No, sir.
All right, do me a favor. Put into your search bar periodic table for me, please. Go to Google and put in periodic table so I can bring up something and show and attempt to answer the question. Forgive me, I don't know why I'm not able to share from this device at all. Same problem with me on the weekend. All right, good. Boy. All right, see if you can zoom in for me, please. All right, good, great. Scroll up now. Let me just see something. Scroll up, the other part of the stuff, up. I want the bottom part of the periodic table. Up, stop. See if you can expand for me now, please. See if you can expand it for me. Now expand it a bit more. A little bit more. One. Oh, good. Up now. So if you look at the 92nd element, the 92nd element with symbol U is uranium. Now, what number is at the bottom? 200 what?
238.029.
238.029. So it means that uranium 238 is the stable form. Sorry. Yes, no, that's 238 or 235. I can't see. What is it?
38.
238.
Right. So that could be the most stable of the forms. And then the other one though is going to be the 235, which is going to be something that is going to be unstable. Scroll up for me to carbon for me, please. Go up to the top part. Carbon. Carbon is what number at the bottom? Carbon is the 6th element. What is carbon there?
12.
12.
12. And remember, we talk about carbon 14. We talk about carbon 14 dating.
Yeah.
So carbon, right? So carbon 14 is going to be the isotope. Carbon-12 is the more stable of the forms. All right. Let us look at rubidium. Go to rubidium for me, please. Let me see. Rubidium? It's number 37. Rubidium here is how much? 80, how much?
85.
85.
Rubidium is 85. All right. Stop share 1 minute, please, Asia. I will come back to you with that. Stop share 1 minute for me, please. And let me just share something to show you what is happening here. So rubidium that is seen on the periodic table is rubidium 85. Agree, true or false?
Yes, sir.
This here now is rubidium 87. So this is the most unstable form. So this is the isotope of rubidium, right? The original element. Sorry.
Sir,
It's going to be.
when you say unstable form, you're suggesting that it doesn't last long?
It's very reactive. It's very reactive. And right, it doesn't last long because it reacts with anything that it gets into contact with. So the unstable form, you have to be very careful with it. You know what comes to mind a while ago? Arsenic, plutonium, arsenic.
Anthrax.
Arsenic. Huh?
Anthrax?
No, man, not anthrax, no, arsenic.
Okay.
Was it arsenic? Actually, yeah, it was arsenic. We had I saw a live sample of it once that grows, it literally grows spores. And you could see the spores just dangling, moving up and down. And we are saying that, you know, if you inhale it, you know, you.
And I sound like anthrax still.
Well, anthrax does the same, has the same property because I mean it will just kill you. So the moment I saw the stuff and they're saying that it is very dangerous, you have to handle it here, I'm saying to myself, I will not die that way. So I made an about turn and I did not look at that sample, none at all, right? It is very unstable. So anything it gets into contact with, it is going to react with it. So the isotope is the most reactive form compared to the stable form. So which is why I showed you the whole business of sodium just now. Sodium in its natural form 2,8,1 with 11 electrons in its outer shell. Well, 11 electrons. The outer shell has 1 with electronic configuration 2,8,1. And that is stable. That is a stable atom. So the atom itself is stable. When it becomes ionized, either it accepts or it gives up or it becomes a different form of the atom. That's when it becomes very reactive. And the reactivity increases because it is now ionized. So in its natural state, it will just exist as it is. It can sit on the side somebody and nothing happens. But the moment sodium becomes ionized, remember the number of protons and the number of electrons in the nucleus does not change. Cannot change. What changes is the electrons in its orbitals. And as a matter of fact, I must hasten to say that it's only the valence electrons that are affected. The valence electrons are the outermost electrons. Those are the ones that take place in the chemical reaction. Now, when that either gives up or accepts, it throws the equilibrium out of whack. Therefore, it becomes an ion, an ion, that ion becomes very reactive. That ion becomes very reactive. And the reactivity means know that when it gets into the presence of chlorine, it forms the compound sodium chloride. And when sodium chloride is formed, it becomes a very stable compound. So you may say to me, then sir, how can something very reactive then reacts with something that is also very reactive, which is chlorine, the chlorine ion? But when both come together, it forms a stable compound, which is sodium chloride. And you and I use sodium chloride every day, which is our table salt. We use it to wash, clean, cook. It is used as an antiseptic, whatever the situation is. So the point I'm making is it becomes so unstable that it increases the reactivity that it can undertake this sort of radiometric dating to pretty much decompose whatever structure. If it's going to be a bone structure, to give it break it down into its core to give you different half-life readings. How it works is, I wonder if I can find a video and show you. All right, I'm going to see if I can find a video to show you exactly how the isotope itself works in getting the, all right. Okay, so Mikey just spoke about anthrax just now. When you're looking at electrolysis, when I'm electrolyzing something, and you may say, sir, electrolysis, how does electrolysis get into geology? It's there. Let me tell you why. Mikey sent something in the group the other day about people in, was it Clarendon, Mikey, who found gold?
Yes, sir. Yes, sir.
Right. Now, when they electrolyze that pyrite, they are going to be using a substance called, I think it's arsenic, or cyanide as one of the constituents as the electrolyte. Now, what happens is it is able to transfer electrons, and I don't want to get into too much chemistry. We have anions and cations, and it is able to transfer electrons from one pole to the next. Now, by a displacement reaction. Now, what happens is when that displacement takes place, the impurities inside of that pyrite is going to fall to the bottom as a sludge. And trust me, you literally see it falls into the bottom of the container as a sludge. The chemistry that takes place inside of it is heavy chemistry that takes place in terms of all those reactions, right? But what you can see is the removal of the impurities from the pyrite at one pole and the formation of pure gold to the other side of the pole. And the point that Mikey was making, which is a point that I've made earlier in class, which is why I guess he posted, is that based on the impurities inside of it, you're going to have this much impurity and this much gold. So which is why we're saying to you that it is not in mineable quantities. It really isn't in mineable quantities. No, the chemistry that takes place in the radiometric dating is a lot of chemistry. But what I'm going to show you is a video. I'm going to find a video tonight. When class ends in another couple of minutes, I'm going to find a video and I'm going to send that video off to you so you can actually see what happens in the radiometric dating process, right? Using the radiometric forms of the atom. And the three types that are used, remember now, If you say in the multiple choice question or in it, remember the 3 types that are used: uranium, carbon, and which one? One that has 40. Start with P.
Potassium.
Potassium, right? So those are not that you don't have anymore, you know. You have some others out there also, right? And potassium 40 here is, go back for me, Asia, please. Let me stop sharing and go back to and show you something. Please stop sharing. Go back to the periodic table for me, please, Asia.
Sorry, so the potassium 40 would really test age like plants.
Cool. Yeah. Go to K. K is number 19 is potassium, right? And if you look at the bottom of it, it's 30. What is that number at the bottom, Asia?
39.
39 point.
39.0.
39.0.
09.
All right, so 39.09. This periodic table is slightly off because. Oh yeah, no, it's fine. Because the calcium is at 40. Good. So this supports the point that I'm making. So the potassium is going to be 39.09, I think it is. Potassium 39 is a stable form. Potassium 39, yes, 39.098. Potassium 39 is a stable form. Potassium 40 is the unstable form. Because it now has one more. 39 to 40 now has one more than it's supposed to have. Carbon
so that's
12.
why the +1 is at the top.
Very good. Carbon 12 is going to be, compared to carbon 40, has 2 more. So it becomes more dangerous. Rubidium has 85. And then now, well, the +1 over here is suggesting, Mikey, that it has 1 electron in its outer shell. And if you look at the one beside it, like magnesium, you see all of those in that thing has 2 electrons, +2 up there. It means that it has 2 electrons in its outer shell. And the one like scandium and on the others there, in the third one, in the where you see the 3 there, it has 3, and the 4 has 4, the 5 has 5, the 6 has 6, the 7 has 7, the 8. Here, inside of here, you're going to have transition elements. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, all those are transition elements. So if you look at it, this is chromium, you have the chromium 6 and the chromium 3. Manganese 7, manganese 4, manganese 2. Iron 6, iron 3, iron 2, right? So you have the different states of those. So if you scroll over to the other side for me, Asia. Right, good job. Right, so if you look at number 13, if you see 13, where you have boron, aluminum, gallium, you will see +3, +3, +3, and you wonder why is it +3 when it is 13? The first shell can hold 2, the second shell holds 8. And then the last shell will hold 3. So every one of those, aluminum, all of those, boron will have 3 in its outer shell. And carbon now, carbon is going to be 12, which is 2, 8, which is 10. So it will have 4 electrons. So is what it says there? You have carbon 4, it has a +4 state, the +3 state, the +2 state. So carbon has a whole heap of different, thank you, sweetheart. You're such a darling. To scroll over now, honey.
So I'm trying to scroll over. I can't scroll over.
You can't scroll over?
No.
All right, you have to reduce it a little. Right. So carbon has so many states that carbon has. Carbon has many different states. Right? So the carbon 14 is going to be the unstable one because the carbon 12 is a stable version. So the carbon 14 is the isotope, right? So the carbon 14 is the isotope. Potassium is, go ahead.
I can ask a question. kind of sound
Mhm.
ridiculous in my head still, but me gonna ask nonetheless.
Go ahead. Go ahead.
The at the top of each column, you have 1, 2, 3, 4, up to I think about 18.
Mhm.
Are those number the representative of the isotope?
Mm-mm. Those
Oh.
are the the number of electrons that are contained in the atom.
So I'm talking at
Not,
the top of
not,
the each of the columns, you know, not in the individual atom, you know. Yeah, those.
right. So what those are saying, so the two, all those are groups. So you have all of those, that's what is group 2. So all these elements, beryllium, magnesium, calcium, strontium, barium, radium, all those are group 2 metals. All those are, and incidentally, the periodic table is broken up into metals, non-metals. You have the transition elements in the middle from 3 to 12. You have the halogens and you have the noble gases, right? So all the ones up top are telling me they have 1 electron in its outer shell. All the 2s are telling me that all those elements have 2s in the outer shell. So how the periodic table is arranged is based on similarities. So all those in the first column, from hydrogen, lithium, sodium, potassium, rubidium, caesium, francium, all of those have 1 electron in its outer shell. So it's not a stupid question, it's an observation that we are making, have 1 electron in its outer shell. So those are called metals, because all those metals will give up that 1 electron in order for it to be ionized. It is easier for it to give up that 1 electron in order for it to be ionized, right?
Question,
And that
sir.
brings, I'll come into you, Asia, 1 minute. And that brings me to the point that I'm making. So rubidium, for argument's sake, is 85. Rubidium will give up 1 electron to become ionized. All right. It means then that the mass number of rubidium is going to still remain as 85, but the atomic number, which is 37, right, which is going to be 2, 8, all of these with 1 electron in its outer shell, it means that rubidium is going to, in order for it to become rubidium 84, I think it was rubidium 87, sorry, it means that it's going to accept more electrons. So it therefore makes that that atom itself become very unstable. I don't know if it's where I'm going, right? It becomes very, very reactive, extremely reactive. Go ahead, Asia.
So sir, you're saying the numbers at the top are the group numbers?
They are, no, the group numbers will be the ones that go from left to right. No, the group numbers are going to go from top to bottom. So these are group 1 elements. So the ones that go from left to right tells me how many orbitals I have. So like lithium now going to have 2. Lithium will have like 2,1, but the ones going down from top to bottom will tell me the group numbers. So they are group 1 elements, then I have the group 2 elements, then I'm going to have the transition elements in the middle, then I'm going to jump over to boron, that is going to be group 3, then we have group 4, very good, which is a carbon, group 5, nitrogen, group 6, oxygen, group 7, fluorine, group 8, starting with helium. The group 8 elements are those that are noble gases, right? Neon, helium, argon, those are things that are noble, very, very stable. So when you go to places like New York in particular, and you see all those neon lights, yeah, man, it's a 10th element of the periodic table that they use inside of it, brightly colored. Matter of fact, they don't need street light in a New York, because all the buildings all have their own neon bulbs going up, bright. All when at midnight, if you don't know say it's midnight, you don't even know that it's midnight, because people are walking like it's daytime, right? New York is always very well built, right? Helium is so light that what they use is helium-filled balloons. You know, when you're talking about your declaration and so forth and so on. Yeah. And when you talk about the group 7 metals now, those are not metals, the gases. Fluorine, chlorine, bromine, iodine, astatine. So those are, start off with gases, the fluorine and the chlorine. And by the time it reaches bromine, is a liquid. And some will say that the chlorine is also a liquid, so it's a change of state. So the fluorine is really a gas. Chlorine is a gas changing into a liquid with bromine. By the time it reaches iodine, it becomes a solid. Astatine is also a solid, right? So it changes state here. Those are halogens, very reactive halogens. And the ones in yellow are going to be my non-metals. And the ones in blue, boron, silicon, germanium, arsenic, all of those are going to be my metalloids. They behave like metals and non-metals, right? Because when they talk about silicon, it's because silicon has 4 electrons in its outer shell. Silicon will not necessarily accept or give up those 4 electrons. What they will do is pretty much share those electrons because they are metalloids. They have both metallic and non-metallic properties to it. Whereas the others, you know, like the non-metals, like the carbon and nitrogen, those will share or accept. The metal ones will definitely give up, right? The halogens, unreactive because they are so stable. They have a field octet, negative part in a number, right? Very stable. The fluorine, chlorine, bromine, iodine, now on the other hand, because they have 7 electrons in its outer shell, they have just 1 more electron to get, so they react very explosively, which is why the halogens and the group 1 metals react beautifully, because the group 1s have only 1 electron in its outer shell, and the group 7s have 7 and just need 1. So you can have lithium oxide, lithium fluoride, lithium chloride, right? Potassium fluoride, potassium chloride, potassium bromide, potassium iodide, right? Sodium bromide, sodium chloride, sodium fluoride, sodium iodide. So you have all of these group 1s reacting very nicely with the group 7s, right? And incidentally, this periodic table accounts for what it is that we have for those many millions of compounds that we have. See them right here. This is a periodic table. And you see some of them, like you see 57 to 71, you see that it is blank. Some of those have not yet been discovered. Scroll down for me, please, Asia. So there are some other metals, some other elements, right? Some other elements in the periodic table. Okay, so when you say 89 to 103, 1993, 94, 95, 96, 99, and 100, 1, 2, 3. All right, some of those here are within that particular range because you still have those elements that are, you know, I won't even say discovered, but are being discovered, so to speak. All right, so yeah. So this is what it is. As I said before, in terms of looking at the working process to show you how the isotopes work, you'll have to see these chemical equations that take place to show you that it moves from one stage to a next stage, and then the outcome is going to be read by, could be like a mass spectrometer. And the mass spectrometer will tell you what half-life reading is going to be, right? So it's something that is done electronically with all these half-lives that are stored inside of the stuff. I know it's 9 minutes past. I'm gonna finish in another 2 minutes. Asia, can you stop share for me 1 minute, please? Let me see if I can find, thank you, hon. Let me see if I can find, I was trying to, I was trying to find it's just one half-life drawings. All right, let me just share this and just end right here. Share screen. All right, so these are my half-life graphs. All right, so for example, all right, so cobalt, CO is cobalt. Let me see if I can click on this and bigify it. Oh Lord. Plutonium is another one, plutonium-243. You remember I was saying to you at the start of the stuff that they were trying to carry plutonium through the Caribbean at some point in time. And the people in the Caribbean says, oh, hell no. Because if that ever comes.
Yes, and Cuba did start lick out and say, not in our waters.
Definitely not in
Then
our
Jamaica
waters.
join in and thing. Yeah, I remember.
Absolutely.
1995,
96.
yeah.
Yeah,
Right.
man. I remember all too well. Let me go back. That's not what I want to know. Oh crap. All right. So so if you look at these half-lives, see if you can look at the big one here. This is cobalt. So what happens is this is a number of half-lives. One half-life is going to be equal to 5.27 years. All right. So in the system itself, you have several of these half-lives that are stored, and the computer will automatically just relate what the half-life of the radioactive material is. So it tells you the age of it. So I see something here that I need to. I'm gonna go back to that one and show you something. All right, let us look at this one here. So if when you do your test and it comes up to this half-life is telling that it's going to be within 10 years. All right, in 10 years. If when you do your half-life and you come to this piece here, it's going to be in 25 years, right? Because what it does, it measures the rate of decay. So when someone dies, for argument's sake, what it does, your body starts to, your half-life, the half-life within the body starts to break down and starts to decay. So they use carbon-14 to measure the level of decay in a mummified thing, for argument's sake. So when it measures the decay of it, it puts into the system things like this to say, okay, this is done. This is a level of decay. So this is what it is that you have today. So this is, and incidentally, in our system, you and I are now living, we have a certain amount of decay that is taking place. So here, where it says today, it means this is where we are. In a couple of years, this is what our half-lives are going, is decreasing. So if when you do your test and it comes up to this portion, you know that from the reading, it tells you from the system that it's going to be 25 years. So what it does, if I do like a terracotta pot, I can tell you that this terracotta plot is 25 years old. As it relates to the exact time the terracotta plot was created, I can't tell you, but I can tell you that it occurred. It came about 25 years ago. Don't know if that is making any sense. Is it? Is it not?
Yes, sir. So basically in a reverse, kind of reverse
thing.
reverse engineering kind of thing.
Yes, that's what it does. But as I said, I'm going to see if I can find, I'm going to find, and let us look at this one also. What this one does is that it is plotting it is plotting the half-life. So these plots that you see in here, it is data that the system is given that it is plotting. So this is a graph that is plotted from whatever artifact that you are dating. And then this graph now is going to be compared to many different graphs that I have in the system. And whichever graph that this graph here, quote unquote, superimpose, it gives you a date. How long is this after? It may say to you it's 100 years. And then you can know that whatever you have just dated is going to be 100 years old. Right? So it's a comparison of what occurs. It's a comparison of what occurs. All right. Anyhow, I'm going to see if I can find that video and send it off to you. And I will definitely need to have a conversation with you based on the development I saw in the WhatsApp, so we can have conversations about the other pieces to come, or the presentation for Wednesday. Is your management classes done now? You had a class today?
No, it's finished.
HR, sorry.
Yeah,
HR
it's
is finished?
Yep.
So you're not going to have any HR on Wednesday
On
either?
Wednesday, no.
Okay, so I'm just putting you on guard. I'm going to ask you to really think about it. I may or may not utilize some of your stuff, because it will be the final class, and I just have a little bit of wrapping up to do. I think pretty much you did pretty well in terms of covering some stuff, but based on the question, I didn't plan to get into the chemistry of it, but I thought it being very useful because you may not have a chemistry background, as was said earlier, in terms of how and why is it that these radioactive atoms are so very reactive, is because it falls outside of the state, the natural state of the atom itself, right? Carbon 12 to carbon 14, uranium, this uranium, that potassium 39 to potassium 40, all right? But I'm going to find something and send up to you. So it is that you can have a look at it. Paz never came to class because in the says I'm not turning on a camera. But thanks for those of you who turned on a camera, and
Oh, sorry, he said that his email is not working, so he couldn't log in.
Oh crap.
Yeah.
All right. Have a good one. Be good and be safe. Thanks for coming out.
Same to you, sir.
Bless up. Cool.
Bye, sir.
Bye-bye, honey.